Okay, welcome back everyone. So we're on our sixth video today where we're talking about building ray tracer. So yesterday we released a video where we implemented the metal material type, and we ended up with a final scene sort of render here where we had two spheres that were metal, silver and gold, and our Lambertian surface or Lambertian material in the middle, which is just a matte diffuse material. And we rendered this in a higher resolution, and 800 by 400, so still pretty low res. But I think you think you can sort of see that this is starting to have some promise, isn't it? So we originally trying to get metal and dielectrics built yesterday, but we didn't get to dielectrics. That's okay. We spent more time refactoring the code base. Go and have a look at that video in the previous video on that. We're going to do dielectrics today though. We'll get there. Actually, if we look at this, dielectrics and positional camera, we might get both done, but we'll certainly do dielectrics. So dielectrics are pretty cool. They're materials that introduce refraction. Okay, and so what this will mean is we can implement things like glass or diamond or even water-like properties. And so the idea here is that we just need to implement some new maths to handle refraction, and we go through something called Snell's law. So if you've done any high school physics or any physics, like that, you will be familiar with Snell's law. The main thing here is that we have this idea of a refractive index, which is represented as n prime there in the formula, and air typically has a refractive index of 1. And other materials have a higher refractive index. So you'll see that the code base that we're following along in the tutorial builds this refract function, and it uses that to work out whether something has been refracted. Builds something that says whether or not something has been diffracted, returns true or false, and also implements or builds the vector of the refracted ray. So that's pretty cool. And then we'll also build this dielectric material as well for our scatter method, or in our case a scatter function. The attenuation is always 1. That's because there's no absorption, and we'll try this out and we'll play with it. They also implement something called a Schlick function. It's a polynomial approximation of reflectivity. So rather than try and model the light ray in a physically very accurate way, we do this simple approximation. So we implement this thing as well, and then we add that to the dielectric material implementation for scatter. So that's going to be a bit of fun. And we can see that if we get a refraction, then we work out what the reflection probability is based on this parameter that we pass in, or this parameter that sits on our material. Now that parameter is our I think it's our refractive index. So it's something that we will keep inside of the material when we build it. And so we'll end up with something that looks really pretty like this. We'll do a higher res render, but we'll get something that looks probably like a lot like that, or maybe slightly nicer at a higher res. Okay, so let's get started. If we go back to our material here, you can see that what we decided to do was put all our materials in a Rust enumeration rather than build abstract classes. And so far that's working out okay. We may have, I don't know whether this will be more efficient or not. I think it probably will be just as fast, if not faster. We did make some other refactors yesterday that made that we were returning a hit record inside of an option, and I'm not sure of the performance implications for doing that. But anyway, we'll continue with this approach until we find a good reason to do otherwise. And so in this case, we have a property that we need to implement. So well, firstly, it's building. Let's build this refract method. So, okay, we've got function refract. Now this takes a whole number of arguments again. So just type those out. Ni over nt is a float. Okay. Now what we're going to do is build a unit vector off v, so we'll say let uv equal 3 unit vector of v. Going to build dt, let dt equal vec3 dot uvn. uv needs to be a reference. Okay, then we need a discriminant. Ni over t times by ni over t times by 1 minus dt times dt. Okay, so this is our discriminant formula. Okay, and then what we say is if the discriminant is greater than 0, then refracted, so refracted needs to be mutable. Then refracted is equal to ni over nt times by uv minus n times dt minus n times the square root of the discriminant. Looks good to me. Okay. T is float 32, n is vec. Cannot multiply float 32. Oh yeah, okay. So we're going to have to dereference n in that case. Okay. That looks okay. And then we return true. Otherwise, we return false. And that means we need to return bool for our method. Okay. That all looks good. Okay. Well, might as well just make it obvious. Okay. So now we have a refract method. And basically it's going to work out this maths. It's going to work out ni over nt times by uv minus nt. Okay. One troublesome practical issue is that when the ray is in the material with a higher refractive index, there's no real solution and no refraction. Here all the light is reflected, and because in practice that is usually inside solid objects, it's called total internal reflection. This is why sometimes the water-air boundary acts as a perfect mirror when you're submerged. The code for refraction is thus a bit more complicated than for reflection. Okay. Now what we're going to do is implement our scatter method for our dielectric material. But in this class, they've stored the refractive index. So we'll go and do the same thing in our material up here. And so we're going to have something which is, I guess, a float. So we'll call it ref index, and it's a float. And so when we go and build our scatter method or scatter function for this, we need to match on the refractive index. Okay. We now have a method here. So we'll say return true by default. Okay, and so now we need to implement this method. So it looks like we've got something called the outward normal, which is just going to be a default vector. So we'll just do vec3 default here. We need reflected ray or reflected vector, which is going to be reflect of ray in direction, and also the normal of the hit record. Okay. Okay, so do that. Okay. I think reflect needs this to be a reference. Okay. Then we're going to build a float. So this needs to be ni over nt. We'll just make that 0 for now. And we'll also do an attenuation, which is pretty straightforward in this case. Oh, and we also need refracted. Wow, okay. So this gets us set up. Now then what we do is we say, if the dot product of ray in dot direction and rect normal is greater than 0, then the outward normal is equal to minus rect normal. And that means that this needs to be mutable, and it also means that we need to implement this unary operator. So we don't have a way of negating a vector, so we need to go into our vec3 class or module, and we need to implement, what do we implement here? Standard ops neg. Okay, so implement ops neg for vec3. Now I guess it should just be, well, what does it need to implement? Function neg probably. Function neg of self. And it should return the same sort of deal. But let's see what it wants. Okay, I think it should just be like this. So we should just be able to return a new vector where we take itself, E0, and negate it. And I think we should just be able to do that for every element. So we can just do that, because I'm lazy. We can just do that for, well, what did I just do? For every index. That should be all we need to do there, and that just returns the vector in the other direction, or the opposite vector. Okay, so we can now negate. That seems fine. Now we were writing unit tests properly and doing all that really well at the start, and we've sort of lost our way a little bit with testing, and we should go back and fix that. But that's okay. We can do more. We can do more unit tests later. So what have we got? We've negated it, and then suddenly n over it becomes the refractive index. Okay. And so if we don't get the dot product greater than 0, then the outward normal just becomes the normal for the hit record. Ni over nt becomes 1 over the refractive index. Okay. Now so this was for reflections, I think. So now what we want to do is we want to check refraction. So if we get if this returns true, so refract ray in dot direction outward normal Ni over nt and refracted, okay, outward normal needs to be a reference, and refracted needs to be a mutable reference. Okay. We're never touching attenuation, so attenuation is always 1 because we don't absorb, so that's fine. But what we need here is, if this is true, then we need scattered to be a new ray, from the same origin to whatever the refracted ray is. Nice. Okay. We need to dereference that so that we can update scattered. No. These don't take references. I really need to make these APIs consistent, don't I? All right, and so that's true. And then so if that doesn't match, then the scattered ray is just the reflected ray. That's all pretty straightforward, isn't it? And then we just return true. So we always scatter. And it's just a question of whether or not we scatter with a refracted ray or if we scatter with a reflected ray. And that's all pretty easy, isn't it? Nice. Okay. So this had nothing to do with the reflection. This was just setting up what we needed for our call to refract. All right, so that looks pretty good. Attenuation is always 1. It will also kill the blue channel. Oh, okay. So this was wrong. That was meant to be a 0. Okay. Now what we're going to do is go back to our main function, our main program here. And we had a whole bunch of different numbers here. So we're going to rebuild all of this by the looks. So what I need is 0.1, 0.2, and 0.5. Okay. That looks right. That was changing that material. This one looks 0.5, 0.8, 0.6, 0.2. So fuzz is 0 in this case for the metal. And so this one's obviously, this is going to be our glass looking thing, so we'll do dielectric here. That only takes the refractive index, and that was going to be 1.5. Okay, so if I've got all that right, we'll do a render. So let's just see. If we render this, what do we see? We should see something like that. So we'll go and reload. Oh wow, okay, that doesn't look right to me. So what have we got here? So we've done exactly the opposite. We've got a bug that you know, is basically not reflecting anything. Okay, so I think we've set up the material okay. It's a dielectric with a refractive index of 1.5. So the position looks right. So it must just be a bug in the material that we've implemented here. So let's have a look at refract. Okay, so I don't think it's the refract part. I think it could be the reflection. I don't know for sure. So the refracted, reflected, we need to say return false here. Okay. So it returns false if it's reflected. Interesting. Okay. That's probably what it was. Let's try again. And we're rendering in a higher resolution so that we can see something that looks a little bit nicer. Let's see what we get here. Oh, same thing. Okay, so that didn't fix it. Let's go back to a lower resolution. Back to our main program. Do 2 and 1 again. We're going to get much faster renders that way. Okay, so we've still got our bug. Excuse me. What are we missing? Okay, so let's go back to our material. So for our dielectric material, we have an outward normal, we have reflected, we have Ni over Nt, we've got this attenuation, and we've got a refracted vector. If dot ray in direction and normal is greater than 0, then the outward normal is minus the rect normal, Ni over nt is that. Outward normal is rect normal. Ni over nt is that. If we get a refraction for the ray in with the outward normal, Ni over nt, passing in the refracted vec, then scattered will become the refracted ray. Otherwise scattered becomes the reflected ray, in which case we return false, otherwise we return true. So that looks good. Okay. Now the other thing I implemented was this negation. So that looks fine to me. Let's just double check how they did it. So negation. What was it? Here. Yep, it's just element-wise negating, which is all I've done here. Looks fine. Missing something. Okay. Attenuation. Attenuation should be modified, not so I was overriding it. That's definitely a problem. Just as scattered is overridden, so that looks good. Let's try again. Okay, that looks better. Still picking up way too much green here. Going to check what else I've done here. What am I missing? Something obvious. So let's have a think, right? So well, let's just try with that. Okay. So that's when we leave the blue channel in. Try the way it is and then change it to see the difference. We'll also kill the blue channel, which is the type of color bug that can be hard to find. Okay, so I assumed that we should have gone with 110, but it looks like this is rendering with 111. Okay, neat. So I think we've kind of got what we wanted there. Now what we're going to do is go to the next section. So we're not finished with the dielectric material yet. So the next bit is that glass has reflectivity that varies with angle. Okay, so to do that, we're going to implement this Schlick function. So let's do that down here. Function Schlick, which takes something called cosine, which is a float, and a refractive index, which is a float. Let R0 equal 1 minus the refractive index divided by 1 plus the refractive index. And then R0, we basically square it. And we return R0 plus 1 minus R0 times by 1 minus cosine to the power of 5. So this is our polynomial. So it's r squared plus 1 minus r squared times 1 minus cosine to the power of 5. Okay, I'll believe you. Let's have a look. Schlick function. So we're implementing this thing. R plus 1 minus r, 1 minus cos theta to the 5. Okay, so here n is 1. Very cool. Anyway, all right. So what we'll do is we've got our Schlick function now, and it returns a float. And then what we're going to do is go up into our dielectric and implement that. So let I'll just set these to 0 for now. These are mutable. Okay. So here cosine is going to equal the refractive index times by the dot product of ray in direction and the normal divided by the ray in direction length. Needs to be a reference. Okay, so we've got cosine need to build cosine in this case. Cosine is equal to whatever, not minus vec of dot. Oh my goodness, vec of dot ray in dot direction normal divided by ray in dot direction dot length. Okay. Alright, that looks good. So we've implemented this bit. And now what we need to do is replace how we're doing our reflection. So in the case of getting a refracted ray, okay, so we're going to just do reflect probability is equal to 1. Else reflect probability is equal to what? So I was wrong here. Misreading. It's going to be the Schlick of cosine and the refractive index. Nice. Okay. And then what we're going to do is if, now we need a random number again. I think we're already generating that down in here. So we'll do the same thing. Goodness gracious. RG. So what are we going to do here? I'm going to say that if what's it complaining about? Good God. What have I done here? If refract ray in dot direction outward normal ni over nt refracted. Okay, this needs to be refracted needs to. What am I doing? I've already got that. Not paying attention. Let's just kill all this. This is killing me here. Okay. Let's just make sure we've got this right. Mismatched bool found. Okay, so if we get the refraction, then we specify the reflected probability. Okay, then what we need to do is we need to generate a random number, and if that random number is less than reflected probability, then we build scattered and So I think we've got that right. Okay, let's just double check. That was a bit messy. So we built our Schlick function. And remember, the Schlick function gives us more of a realistic effect depending on the angle that we're looking at. And then we're going and implementing that by building a reflect probability and a cosine. The cosine is passed into the Schlick function. The cosine is built differently depending on whether or not this is true or false. Then we're doing the refract, and if it's refracting, then we do Schlick. If it's not, then we say the reflect probability is 1. And then we go and build a random number between 0 and 1. Okay. All right. Let's see what happens. So if we go back to our main function or our main program here, we now have, what do we got? Let's look at this. I don't think it's changed too much. Well, the third one has. We need 0.3 fuzz. Dielectric. One more. So this is a sphere with a negative diameter. So an interesting and easy trick with dielectric spheres is to note that if you use a negative radius, the geometry is unaffected, but the surface normal points inward, so it can be used as a bubble to make a hollow glass sphere. Very cool. All right, so let's try that. That looks really interesting. Let's render that at a higher res. We'll go back to 8x4. Okay. Pretty. So we've still got our nice gold metal surface, our Lambertian, and now we've got this really nice glass-looking dielectric with looks like a glass bubble. And if you look at the edges, you can see. Well, firstly, you get this really nice distortion coming through from the glass, but then you also see this kind of. Is this a combination of refraction and internal reflection? Not sure. Okay, so anyway, so that's the dielectric finished, which is pretty neat. So that's up to section 10 now. So I'm going to stop there, just keep the video short. In the next one though, what I'll do is I'll build the positional camera and the defocus blur. We'll do that in one go. And that's really the last part of the ray tracer. So that'll be a bit of fun because we'll end up being able to move the camera around and get a different view or a different perspective. Remember the surface that we're rendering here, it looks kind of flat in these images because we're so close to the scene, but also close to the objects in the scene. But when we start zooming out and changing the camera angle, we'll notice that this is in fact actually a very large sphere. And we'll get these beautiful effects where the light bleeds into the edge of the surface of the glass ball here, and it will look a lot more three-dimensional, which is pretty cool. The defocus blur is basically depth of field for anyone that does photography. So the larger the aperture, the more depth of field effect that you get, just because of the way that the light focuses on a larger aperture. And so we'll build the concept of a lens. And we don't build a lens class or anything, but we implement the camera, as though it has something like a perfect lens, or I think it's called like a zero thickness lens or something. Anyway, and so we'll build that, and then we're done. And so then the last bit really will be building this last scene. Now I've already gone ahead and done that, and it renders beautifully. I've rendered it at high res, and you can see that on the GitHub repo. So if you wanted to follow along, look at the GitHub repo. This is actually a render that I put together because I finished the ray tracer just to kind of go ahead, and it looks pretty spectacular. It's pretty cool to see that come out. I rendered that at pretty high res though. Took quite a while. Took a couple of minutes to render that, believe it or not. But part of my favorite of this scene is kind of looking at the material there with the fuzz on it reflecting, and my goodness, it's just neat. Anyway, so we're about one video away from that. And we'll go through and finish that next time. So look, thanks again. This has been fun. I'm trying to do shorter videos so I can get them out faster, and expect the next video covering positional camera and defocus blur probably tomorrow. I'll get it out tomorrow. I might even try it tonight, but let's say tomorrow, and then we'll finally get this final scene done, and we'll sort of be done. And then I think after that, I'd like feedback if you want to see something else on the ray tracer. There are 2 more books that come after this that take the ray tracer a lot further along. I would love to, before I consider doing that, step back and look at the actual theory behind this. There's quite a bit of simple maths, but just understanding how all that interacts, I think, is going to be worthwhile, and maybe that's a video in its own right. I could probably draw out my understanding of that using a tablet that I have here, just so that we sort of have more of an interactive kind of session on what the theory actually does. But regardless, if you like this video, please don't forget to hit the like button. That tells me that you enjoyed it. And please leave comments if you want to see something different, or you want to point out a stupid mistake that I made, or you have any feedback at all. I value that stuff, and thanks again for watching, and we'll see you in the next video. Cheers.